So this concept of work is not a difficult concept, but it's something that people make mistakes on. And it's based on the concept of the scientific definition. So if you literally were to push an object, you could say you're doing work. Physically, you're doing work. If you were to pick up an object from a table, you're doing work. If you were to walk across the room, you're doing work. Theoretically, so pick up an object, hit this object and move it, walk across the room. But theoretically, if I were to just hold this object right here and hold it still and not move it, I'm not doing any work right now. Again, the first time I pushed it a certain distance, I then lifted this up off the table and put it back down. I then walked around the room. In all of those examples, I did work. But in this example, where this object is already here and I'm just holding it in place, right now, specifically right now, at this instant in time, I'm not doing any work. What's the difference between the scenario right now, I'm holding this, versus all the other three scenarios I just gave you? The first three you did work, and this one you don't do any work by holding it.
You're not moving?
You're not moving. So work involves motion. Good point there, Chris. Work involves motion. Let's jot that down. To do work, you have to have some motion occurring. Whether it's a wheel spinning, and this is the motion of the wheel, or it's an object physically moving linearly, you need motion. You need motion for work to be done. Okay, and that comes from the scientific actual definition. So let's jump right to the second slide here to see that. And maybe Chris picked up on it, maybe looked ahead, but either way, you got the right point, right? Using this context here. So you could have also looked ahead and said, hey, look at the formula. It looks like there's a variable in this formula that involves some sort of motion. What variable is that? What variable is referring to motion of some sort in this case? What do you think? Yeah.
Force.
Force could apply motion, agreed. And then what else? What's the other variable there? What does D stand for? We haven't used D in a while, since like the first chapter. I have not used D. What is D? Distance. And if you move a distance, it infers motion, right? Obviously, if your distance is 0, what does the work become? In the formula, if distance is 0, what does the answer become for work? Yeah, 0 times anything is 0. Even if the angle is something, even if the force is something, if the distance is 0, the overall work will be 0. So you need motion to have work being done. So there's like a very common misconception of the concept that I was trying to show you. Like if you're working out and you go for a run or you lift weights, you're doing work the whole time. You know that because you're expending energy, and work and energy, we're going to see how they're related. But if you physically, say you pick up like a 15-pound dumbbell and you're actually just holding it still, you're not doing any work. It's the lowering and the raising process that does the work. For anyone that's worked out before, worked out, work, you notice that to actually work out, you have to physically move. If you, it's true, but it's not true, because like you ever do planks before, and for like a workout like a plank, you would hold yourself in a push-up position, and you're not really moving, but you're expending energy still there in that sense. But I want you to think about the concept that when you're really exerting energy and doing work, you're actually lifting the weight and lowering the weight, and lifting it and lowering it. Holding a weight right here isn't really doing much besides putting some bad stress on your shoulder. Not doing much besides doing that. You're not actually helping your body and your muscles. So think about doing work as moving. You have to move. Okay, so we're talking about a force that's applied over a given distance. A force that's applied over a given distance. And why do I put this cosine theta? Why do I put this cosine theta piece? We are really referring to the work done in the x, or the direction of motion. So let's talk about this with a quick diagram. Let's go ahead and draw a body with a free body diagram. Let's go ahead and draw a force acting on this. And let's say that the motion is to the right. Remember in these diagrams in the past, I put acceleration showing which way it's moving. So yes, here I do have the weight. I do have the normal force. Okay, that's my real free body diagram. But I notice that if I apply a force at an angle, I keep saying these angles aren't going away. I keep saying it. Okay, it's not going to just miraculously disappear. If I apply this force at a given angle theta, the thing I want to realize is I want to figure out the component of the force. Read again, I'll highlight it at the top. The component of the force along the direction of displacement. And if I think about it, in this problem, displacement is horizontal. Displacement is horizontal, so I'm really looking for the x component of this force, which is really F cosine theta. That's the force I'm using in this formula. So look at the formula. It's already got F cosine theta there for you. Okay, the formula already takes into account the fact that we're going to use the x component when we're looking at these problems. Okay, now theta, if you want to remember, maybe jot this down. This is very good to have written down to help students realize. Theta is the angle between the force. The theta is the angle between the force and the direction of motion. The force and the direction of motion. So you don't really have to do the component part for this problem because it's already in the formula itself. This is assuming, again, that motion is to the right in this problem. And motion is to the right. My formula up here, work equals FD cosine theta. As far as units are considered, force is measured in newtons. D, or distance, is measured in meters. So it's a newton times a meter. Those are my unit analysis parts right there. Cosine theta, there's no units for that. So I know that it's a newton times a meter. And it turns out this is going to be our newest unit of measurement, a joule. Joule, joule, not Jewel. Okay, joule. Joules are measurements of energy or work done. Energy or work done. So write yourself a little note that a newton times a meter is a joule. A newton times a meter is a joule. Don't confuse it with jewelry spelled that way, okay? Please spell it the correct way. It really, when I see miscorrect spellings, it's like, did you do any of the word example problems? Because you're going to see this word over and over again. So if you spell it wrong, it's going to make me think you're just not practicing. Okay? It's a capital J, but Joule if you're going to write it out. Now, if this is one of the examples I want to discuss real quick. If motion is vertical, actually, if motion is vertical, I still use cosine theta. Okay, and let me explain real quick. So let's do another example here on the right. Let's say an object, okay, an object is being pulled at an angle from like a conveyor, on a conveyor belt. There's a little pulley system. And the object's motion is going to be upward. Let's say it's moving upward in this case. There's the conveyor belt with a little pulley system, and there's a force being applied, F. If this is the case, so imagine this is an example like you're lifting something out of like a mine shaft or something out of like a what's it called? Wishing well. You know what a wishing well is? Where the well is drawn with the water at the bottom. Just a well, I guess, in this case. Imagine you had some sort of a pulley system and you were pulling on a cord and it was lifting an object vertically. If it's lifted vertically, the dashed line represents motion now. And the force is represented by this vector. And if theta, as we said a minute ago, was defined as the angle between the direction of force and the direction of motion, then this is theta in this problem right here. Right there, that's the theta value, which is a little bit different than what we've been seeing all year. Most of the year so far, we have called theta the angle between whatever the vector was and the horizontal. It's always been that. But now that we're looking at work has to do with the motion. So if the motion is to the right, then theta is here. But if the motion is up, if the object is physically moving up, then theta is this angle. They are complements of one another. If this angle here, hypothetically, were 60, then this one would be 30. And up to 90. Steve?
So it means that any of the problems, at least for network, we're always going to use cosine.
Yeah, you don't have to worry about sine ever, it turns out. Because we're not going to worry about like the y component anymore. We're just going to switch theta, which inherently switches to the y component, which is what you're kind of doing. But yes, you can remember just to use cosine theta every time. As long as you remember what theta is. Theta is the angle between the direction of motion and the force applied. Or maybe the direction of motion and the force applied. Depends on which way you're moving. And we'll see that with a couple of these problems. Let's take a look at this first simple example. This is work, by the way. Work is one of the easier topics of the year. I find students do very well with this problem. You're going to relate work and kinetic energy in the next section. We're going to talk about that. And that gets a little bit trickier, but it's not that much more. How much work is done on a shopping cart if you pull it 12 meters with a force of 75 newtons at an angle of 60 degrees? Now, if you're not given anything about where the angle is between, you assume it's the angle between motion and the force applied. So think about a shopping cart. You have to visualize stuff. A lot of you are just trying to draw diagrams without visualizing the scenario. If this were the shopping cart and I were pulling on it, not pushing, I put pull in this case. If I were pulling on a shopping cart, I would walk around the grocery store like this, right? I'd probably hold the front of the shopping cart and pull it behind me instead of pushing it. Again, you could push it, but this says pull. So I'm pulling the shopping cart like this. Which way is motion? I'll do it this way. Which way is motion? Is it in the X or in the Y? Which way am I walking? X or Y? In the X. And here's my force of the pull. My arm is the direction of the vector pull. And here's motion. So there's my angle right there. So draw yourself a little diagram of this. Draw yourself a diagram. Free body diagrams are not as used here. Okay, so we're not going to concern ourselves too much with every other force because we're trying to find the work done by this applied force. So a diagram could be useful here to show that I'm being pulled at 75 newtons at an angle of 60 degrees for a distance of 12 meters. So at least I've listed all my givens now with some sort of a diagram. But don't worry about the whole free body diagram anymore. That was really when we studied forces. We're going to see it might play a role here and there, and I'll point out when it does. So in this problem, it's a simple plug and chug. W equals F D cos theta. Plug right in, get your answer. Okay, the cosine of 60 happens to be 1/2. It's one of the angles you're going to learn about this year in math. One of your special angles. So it's 1/2. So this just becomes 6. I do 6 times 75. Okay, 450. What are my units for work? What did we say in the previous slide? What am I going to write as a unit for work? What did we say? Joules. Okay? I'm not going to really go into crazy detail just yet, but I want to point out something, that work can be positive or negative. Work can be positive or negative. Go ahead and do this problem again and try cosine of negative 60 degrees. Use a negative angle. Or try cosine of like 140 degrees. Try an angle between 90 and 180. Actually, don't use negative. Use an angle between 90 and 180 instead. And you're going to see that if you try the cosine of any angle, not 90 itself, but between exclusively 90 and 180, you'll see that it's going to be negative. So do like cos 150, cos 120, cos 130. You're going to get a negative number, right? And therefore your work done will be negative. So work done can be negative or positive. Work done can be negative or it can be positive. We're going to really focus specifically on work done by friction and work done by applied forces. Does friction help or hurt you? Does friction help or hurt your motion? That's not rolling friction. Rolling friction helps your motion. Rolling friction helps your motion. Sliding friction, what does it do to your motion? If I'm sliding and then I stop applying a force, eventually the object's going to... so it's hurting your motion, meaning it's lowering your velocity. So we're going to see in a little while that friction provides negative work. A pull or a push, as seen here, provides positive work. And think about work, we're going to see in 6.2, work and energy. They're kind of the same thing. If I get something moving really fast, when you say it has a lot of energy, think about like a running back in football. A running back that's moving really fast because they've applied a lot of force of pushing their feet really hard for a certain distance. They've accumulated some velocity and they've got a lot of energy. And we'll see kinetic energy in the next section. Now, with that, let's see how work can be negative and positive. So this question says, what would the angle theta be if the force is a horizontal force in the direction of displacement? So no longer a force at an angle, but a horizontal force in the direction of displacement. And then what if that force is in the opposite direction of displacement? So I want you to just think about drawing a diagram first. Just start with a simple dot. Show a horizontal. I'm not going to draw it. I want you to try on your own, then I'll draw it. So start with a dot. Think about a horizontal force. Horizontal means in what direction? Horizontal means in what direction? Which of the two? X direction. So draw a force in the X direction only. God bless you. Then let's show that the object is moving in the X direction. So let's draw a force in the X direction and let's show motion in the X direction. And then let's think about what that angle would be. What's the angle between those two things? if I draw a vector in the x, and then I draw motion in the x, what's the angle between those two vectors? 0 degrees. It's really 0 degrees. So that's the first part. Let's draw this real quick. So again, here's the object. You're applying a horizontal force. Motion is also horizontal. So that means you're going to accelerate to the right. So my dashed line showing motion is literally on top of the force line. So is there any angle between them? No, there's no angle between them. So the angle becomes 0 degrees. Go to your calculator real quick. Go to your calculator. Type in, and I want everybody to do this so you can visualize these numbers. Type in the cosine of 60 first, like we did last time. When you type in cos 60, you're going to get 0.5. Type in cos 20. So you get a bigger number, right? 0.9. Type in cosine of 2 degrees. So you get an even bigger number, right? What is it getting closer and closer to, though? Looks like 1. Type in the cosine of 0 degrees. And you get exactly 1. So this formula, when this is the scenario, this formula itself becomes just f times d. Because the cosine of 0 degrees, this is 0 degrees, and the cosine of 0 degrees is 1, which simply makes the formula reduce to this. This is a very useful formula to write down. You don't need the cosine of the angle when it's applied horizontally. This is like a specific situation, right? A situation that might be good to have in the back of your mind. When the force is applied horizontally in the direction of motion, theta is 0, so therefore you just get work equals FD. You just get work equals FD. I want you to try something else now. That was the first part. For the second part, I want you to think, what if the force was the opposite the direction of motion? What force is applied opposite the direction of motion? What force have we been talking about that opposes motion, Catherine? Friction. So although this was a push, let's call that FP for this diagram, for friction, and let's draw our dot first, friction would be pulling back or acting against motion. Although motion is to the right still. We're still drawing motion to the right. So what's the angle here? What's the angle between acceleration, which is that way, and your force of friction, which is that way? What's the physical number? What's the value of that angle, Maria? It is 180. Good job. Okay, the angle is measured between here to here, and that is 180 degrees. Calculator, let's go. Cosine 180. Cosine 180. There you go. Thank you, Sarah. So this becomes work equals FD times -1, which is really saying that the work done will be negative FD. And that makes sense, because what did I say a minute ago? Friction is going to make you lose energy. It's going to do negative work. It's going to do negative work. So some sort of applied force that helps motion does positive work. So making something go faster, helping motion, these are the same things. Make it go faster, help motion. That means you do positive work. That's usually done by some external applied force. Friction, or something, air resistance, something that slows down an object, slows down or hurts the motion, does negative work. Really important that we see helping motion, positive work, hurting motion, negative work. This is going to tie into 6.2 when we get to that section. Okay, so recognize that you can do positive and negative work. Remember chemistry, you had exothermic and endothermic reactions. Endothermic absorbed energy, exothermic gave off energy. Very similar here. An object gains energy, absorbing, versus an object losing energy, giving it off. Think about it physically. Where does the energy go when friction slows you down? Anybody know? Think about it. Come on. You can figure this out for sure. If friction slows you down, the energy has to go somewhere. In what form of energy does it convert to? Heat. Heat energy. Okay? Friction produces heat. If you've ever taken a paper clip and bent it back and forth enough, you're creating friction between the molecules, and eventually what will happen? It snaps. It gets really hot, and it actually just snaps apart. Another example of this to think is physically about friction. If friction is opposing motion, you have to think about motion being the energy. You're just losing the energy. The heat is the energy lost. You're giving off heat as energy.
When you're like drifting in a car, what is the smoke that comes out?
So that's the actual tires themselves, the rubber that's on the tire burning.
Heating up, right?
So heat. Yep, exactly that. There's another one I wanted to do with this. What was it? Maybe I have it down. Was there another example? All right, let me come back to it. I felt like I had something else in my mind. The next slide shows you simply this concept that, you know what? If you help motion, you do positive work. That's on the right side. Take a look on the right side. On the right side, this person is pulling the car or pushing the car in the direction of motion. But on the left side, the car is moving to the right and the person is opposing the motion. So you could do negative work also. Chris, if you ran at me and I were to just put my hands up to try and stop you, probably wouldn't be able to, but I could try to, I would be doing negative work on you, slowing down your motion. I would be like friction, doing negative work. But if instead, hypothetically, a person catches a pass, a wide receiver, he's running. If a person tackles you from behind, they're actually doing positive work for an instant. They're kind of helping you because they're pushing you forward in the direction of your motion, but they're also pushing you down on the ground, which is that's a whole other segment because you're doing two types of work, vertical and horizontal. Okay, but think about the example of negative work of like a linebacker trying to tackle a running back. They're opposing the motion. They're doing negative work. They're stopping motion. So we have one example to finish off the day, and it's a pretty extensive one. So here's what I want you to do. With the person next to you, simply try to get through parts A, and then if you get through A, check with me, and then when you get with that, go to B after that. But work with the person next to you on part A. We've got a little bit of time, so I'd rather you actually work on this yourselves. So try to do this. It's not a difficult topic. Use what you did on the last slide to help you with this. Okay, use what you did on the last slide to help you. Hey, keep in mind for a problem like this, you may have to do a little bit of work for part B to figure out the force of friction, right? The force of friction for part B. For part A, you have the force already, so you can work with that. But for part B, you got to consider friction. Friction equals mu times Fn, so you kind of have to use what you did in the last chapter.
Probably to find a friction. Because we know the normal. No, that's the friction.
What? Let's try it. Me? I know. it's fine. I just did, I found it to 80 of
Yes.
So like, I'll get the majority of the time. I can't. You see how much I can learn? Oh, I did learn. Wow, 5 pages. What? Oh, we're in the first page. There's only 3 assignments. Yeah. How many pages? 5.
Oh, no.
What? I actually don't want to go into this. I didn't know where to stick that.
You don't want stuff to explain. It's probably regulated by the building, so I'm still not going to really. It's in back pocket. You sat on it. Why would you eat it? You sat on it. Yes.
A is literally
Yeah, I got it. No, yeah, I got it. Yeah. Yeah, you might have to say that. We have like oh, you're not.
Thanks, Steve. Hey, these are some little problem sets. Problem set 3. Steve, you want? Yeah, it's a need for some sort of a doctor's appointment. You told me about it. You thought you just got another guy?
Yeah.
Yeah, they set up for me yesterday. I know. Actually, no one else missed. This was problem set 3. It's an older one. Problem set 4 you just turned in. I have not created problem set 4 yet. Actually, everything else in the sections. Can somebody put up part A? Can I get part A? Just airplay if you have it done. Anybody close? Have it done, maybe? Oops. Sure. Hey, the weight is given, right? The weight is given, not the mass here. So they give you Fg. Remember, Fg is mass times gravity, the weight. The weight of the desk is 20 newtons. That's the weight of the desk. The applied force Fp is what 12 is in this problem. Can we talk then maybe about part A and B? How does A and B differ? Or how do A and B differ, I should say? How do A and B differ? Work done by the student versus work done by the floor. Is the student helping or hurting the desk? Helping. What does the floor do though? It hurts it. It lowers the motion. So the first example of part A should give us a positive answer. And B should definitely be a negative answer. It's a question of what is that answer. So for part A, I have to think about F times D times cosine theta. That's what work is equal to. Well, if I'm pushing it with a horizontal force and it's moving horizontally, what's the angle? What did we say in the last example? What's the angle when I move in the same direction that I'm pushing? Yeah, 0 degrees. So this simply reduces to F times D. I'm going to put a little subscript for Fp because it's the applied or the force that I'm pushing it with. Fp. That's going to go in place and that's going to be 12. So it's simply 12 by 24. And if I wasn't sure what the units are, it's going to be joules because it's energy. Okay, 12 times 24. That'll give me a total of 288. That's the amount of work done by the student on the desk. The question now that's hard is how much work is done by the floor, right? That's the harder part for sure. What force opposes motion again? What force physically opposes motion? Friction. So instead of using, take a look please here, instead of using FP, let's use FF. Is that agreeable? Right? FF is the thing that's doing work, not FP. And if I think back to my statement from the previous slide, we said when friction does the work, what's the angle going to be? 180. So that's what part B gives me. But force of friction, we know it. What's the formula for force of friction? Because we're not given the force of friction in this problem, but we know there's a formula for it. What's the formula that exists for force of friction? FF equals, we just did it 30 minutes ago, right? Yeah, what is it? Mu Fn. And why am I putting -1 at the end there? What's that signifying? What's the reason for the -1? Yeah, cosine of 180 is -1. So I can replace that. Why did I do this? Why did I do this? What do you think?
Because we're given UK,
Yeah.
you're also given FN.
We'll figure that out directly. Yeah. You're not given FF. Please look up. You're not given FF. The force of friction is not given anywhere. But the coefficient of kinetic friction is given in this problem. If I scroll up, I'll see that that's given as 0.2. Okay, that's right here, 0.2. That's the coefficient of kinetic friction. So because I'm given that value, I'm probably going to want to use it in my equation, which is why I decided let's replace FF with its definition. How come I know Fn? Alex said we know Fn. I don't have it written down, but he's right. We do know Fn.
Mass times G.
We don't have mass,
So then it's the weight.
which is, what's the weight of the desk in this diagram? 20 newtons. The desk weighs 20 newtons. Remember, if you're not given the mass, so Isabella, mg is correct, but that is the definition of weight. So if I'm not actually given the mass, I want to recognize that the normal force is just equal and opposite of the actual weight. How come I can say that? Why are they both 20? Why is the up 20 and the down 20? How come they're both the same thing? Yeah. In the y direction. There's no motion or it's constant motion, either one. So the acceleration doesn't matter in the y direction. So we could say Fn minus Fg equals 0. In essence, those equal each other. 20 minus 20 is 0. So that turns out to make my formula a little bit easier. Coefficient was what was the number again? 0.2? The normal force is 20. The distance is still 24 meters. And this is all times -1. You're literally multiplying 4 things across. Obviously, the -1 you can just carry as a negative. Okay, so a fifth of 20 is 5. 5 times 24 is going to give me 120. No, that's not right. Is that right? No. 90. I'm getting 96, right? Did I do something? Yeah, a fifth of 20 is 4, not 5. That's why. 96 joules. It's going to be a negative because it's the work done by friction. So here's my final question, which is really what part C is saying. Part C says, what is the net work done on this object? Net. What does net mean? Now that we've talked about that phrase before. Net. Total. Overall. So here's the work you do. Positive. Here's the work friction does. Negative. If I want net, net means add everything together, right? 288 plus a -96. My answer is going to be something below 288. I know it's going to be a positive answer because 288 is more than 96. So if I want the net work, it's really equal to the sum of all the work done. Remember that symbol? You've seen that symbol already, sum of all the work. Technically, you're going to see in math, they're going to call this WI, where I ranges from 1 to 2 objects. But don't focus yourselves on that right now. Okay, it's the sum of all the works done, so that's equal to the work done by you plus the work done by friction. We'll call the work done by you W1. We'll call the work done by friction W2. So you do 288 joules of work. Friction hurts it with negative 96 joules. When we add those together, we'll still get a positive, but it's going to be 192 joules. So the idea I want you to recognize is that, you know what? Did you overcome friction here? How can you conclude? Did you, yes or no, overcome friction? What would you conclude based on this? Take a stab at it and think about what's happening. Did you overcome friction? Just literally compare.
Yes,
Yeah.
because W1 is bigger than W2.
Hold up. The work that you do is more than friction's work, so you overcame friction. That's why you get a positive answer. If you are able to do more work than friction, you're giving the object energy. So it gains energy. So your answer for the overall work done should be positive here. Should be positive. 24 gives me 90. Again, please practice. Please, there's only 4 examples. That's all I want you to work on for now. We have 2 labs this chapter we're going to do for this. We have a couple sections, 6.1, 6.2, 6.3, and 6.4. So we're going to be going through like a section each day, and then 2 full days of labs. So we have about 6 classes, and then we get to the next test already. So just realize, guys, that we have 3 tests before December. You guys have 2 days off before Thanksgiving for junior retreat, Monday and Tuesday. I see one of the classes Wednesday, and then we kind of get back from Thanksgiving and you have a test coming up. So keep that in the back of your mind, okay? Let's wait 2 seconds at least for balance programs.
Yeah.
They're doing something with music now, actually, right?
Oh, they're gonna play some songs.
That's just the noise. Yeah, so what is this all about? You started this idea of playing songs on Fridays? It's kind of cool. It's better than a bell ringing on a Friday. It's like celebrating the weekend. They make the song or not? What's the song?
Yes! They should play that on the last day of school.
Yes, I mean, it's a nice Friday thing at least. It's celebrating the weekend.